is sample problem 7.4 that's in your text. I just wanted to go through it. So what it's doing is it's asking you to find differences in binding energy and then differences in mass and finally energy equivalents for one of the fission reactions that we looked at, and it's actually the top one here, this uranium 235 turning into 236 and then turning into lanthanum and bromine. So, and 3 neutrons, which are important actually because the neutron contributes something to mass, so it's actually quite important. So the first part of problem 7.4, part A, it says what is the difference, which means subtraction, between the binding energy of uranium 236 and the sum, which means the addition, of the binding energies of the 2 fission fragments. Now that sounds like there's a lot going on, but think about this. This is the formula here. So it's worth writing this down, this formula. We have a starting thing, so a starting element, uranium, and 2 elements that come off, lanthanum and bromine, and 3 neutrons and energy. So it's asking you to find what's the binding energy for uranium and what's the binding energy for the 2 fission fragments, the lanthanum and the bromine. So what we do is we just look them up in the table. So we go back up to your table. You see there's the total binding energy in mega electron volts. There's uranium, lanthanum, and bromine. So we're going to just see, you can see here on this next line, you've got binding energy of uranium taken from the table, the binding energy of lanthanum and bromine here and here, and they've been added together to give you this amount. So when it asks you now for the difference in binding energy, the difference is going to be 1 subtract the other. Make it the positive difference, so take the big number and subtract the smaller number. So you can see here energy difference, and it's 160.000732 mega electron volts. That's the energy difference. Now the next part of the question says what is the difference between the mass of the uranium nucleus and the sum of the masses of all the fission fragments, including neutrons, which is very important. So again, we use the table. We look for the mass of uranium first, and this is in your table in this second column. It's all in kilos. Can you see the mass of uranium, the mass of lanthanum, the mass of bromine, and the mass of a neutron? So tiny. They're all in here. Okay, so we're going to just take them in and put them, write them down for the question. So we want the mass of uranium, 236, which is written down, and then the sum of the masses of all the fission fragments. And check it out, there's 1, 2, 3 things. The lanthanum, which they get from the table, that's lanthanum. The bromine, which is here. And then 3 lots of neutron. And we have 3 times this number here, and this is the mass of a neutron. So all of these things added together is the total mass of the fragments that came off. And check it out, the mass of what came off is a little bit less than the mass of your starting material. So you have a mass difference, and the question is asking you what is this difference between the masses. So we take our original uranium mass and subtract this total mass of all the bits that flew off it. And you can see you have a mass difference. It's very, very small, which doesn't seem like it would be much, but it's going to be really important because we're now going to use E equals mc squared for part C. Use E equals mc squared to calculate the energy equivalent of this mass difference in joules and mega electron volts. Now, energy is related to mass times the speed of light squared. Now, if we know the mass of something, which we do, we know the mass difference, the mass that was lost, and we know the speed of light, we can square it. So if we multiply those things together, we'll get the energy that was lost. And that energy, when we say lost, is the energy output from the fission reaction. So we take our mass difference, which is here, we multiply it by the speed of light, 2.998, or here it's the long version, by 10 to the 8. This is the mass of the speed of light squared. If you put this in your calculator, you might like to put brackets around this first bit just so you know this is one thing, this is another thing. Multiply it all together and you get this answer, 2.563 approximately by 10 to the negative 11. Now this will be in joules, okay, so the energy difference is in joules. And then to turn this difference into mega electron volts, which is what they want you to do, use the formula or use the measurement here. So 1 mega electron volt is 1.602 by 10 to the negative 13 joules. So what that means is if you know how many joules you have, which we do in this question, then all you need to do is divide by that number of joules, and that gives you mega electron volts. Now what you'll notice is it's 1.59.985. If I rounded that, it's about 160 mega electron volts. Check out the answer in part A when we looked at the difference of binding energy, 160 mega electron volts. So what that means is there's actually two ways to find the energy that's released in a fission reaction. You can either directly find the difference in binding energies, and that straight up gives you the energy, or you can find the difference in masses and then use E equals mc squared to get the energy out. Now obviously this second method has a lot more work in it. So if you know the binding energies, it's quicker really to do your sums that way to figure out the energy that's released in a fission reaction.